This is session 6, track 2, 3D utilities for a successful and cost-effective project. I am Samantha Safara, the Marketing Services Manager for HDR, and I'll be your moderator for the session today. Going to go over a few housekeeping items before we begin. So please be sure to utilize the Q&A chat function. It's on the right-hand side of your screen, and that's where you'll post your questions. Dom Yanuzzi will be facilitating the Q&A at the end of the presentation. I'll be posting a link to the lobby in the chat box to use if you need to navigate back to the lobby or go to another track. I'm also posting a link to the PDH form in the chat box. So please fill out during the session if you can. All PDH certificates will be issued shortly after the conference concludes, if not sooner. If you experience any technical issues during the presentation, email the conference help desk at 2021helpdesk@ashi.pro. And now it's my pleasure to introduce your speakers. We have Evan, Joe, Cyrus, and Chanel. They're going to be talking about utilizing 3D utility data to identify utility conflicts earlier in the project cycle, allowing decisions to be made in real time to mitigate costly utility relocations and schedule delays. Evan Dailey is with KCI Technologies. He currently serves as KCI's lead for utility services, including SUE and utility coordination in Georgia. He has worked on various projects, including the Texas high-speed rail from Dallas to Houston and the US 441 corridor project in Georgia, just to name a few. Evan has been in the SUE industry for 8 years and currently works with the Georgia Department of Transportation and local municipalities providing SUE and utility coordination on transportation projects. Joseph.porter is also with KCI Technologies. He is the SUE and UC National QA/QC and Training Manager for KCI. He is an experienced quality assurance and quality control manager. NASCO PACP, LACP, and MACP certified, and NULCA accredited utility locator with a demonstrated history of working in the civil engineering industry, specifically SUE. That's a lot of acronyms. Cyrus McCall is a senior engineer for innovation with KCI. Cyrus brings a unique combination of practical highway design experience, software knowledge, training experience, problem solving, and project leadership to the team. Over his 22-year career, Cyrus has used his extensive skill set to improve operational efficiency at all levels. Chanel T. Gibbs with the Georgia Department of Transportation currently manages the SUE group for GDOT and serves as the state subsurface utility engineer, which manages a group of review engineers and oversees the subsurface utility engineering activities throughout the state of Georgia. Chanel also manages a group of on-call consultants and has played a pivotal role in moving the GDOT Utilities Office into 3D design. Chanel is passionate about cultivating awareness and training for the benefit of subsurface utility engineering for GDOT, as well as consultants and municipalities in Georgia. So without further delay, I'd like to turn it over to Evan, Joe, Cyrus, and Chanel. You may start your presentation. Thank you.
Okay, Jez, let's switch to the next slide here. And Chanel, I'll let you begin.
Okay, good morning, everyone. Again, my name is Chanel Gibbs. So as the GDOT Subsurface Utility Engineer Program Manager, our ultimate goal in utility coordination is to assist in delivering a product while controlling and managing utility risk to the roadway project. It starts in the beginning at concept, through preliminary design, and ultimately through construction. I often use the phrase design with utilities in mind. GDOT faces various utility challenges that I'm inclined to think are similar to what other DOTs deal with. Some of the challenges we face start at the beginning, where we often have trouble obtaining utility records, and when we do, they can be outdated or the information is hard to interpret. As utility engineers, we need to promote constant communication and coordination with our utility partners. Utility coordination is an ongoing process through the life of the project, and when design changes occur, utility conflicts have to be reassessed. I can't tell you how many times I have seen a project go through an initial assessment to identify utility conflicts, and as we all know, design changes occur. Often these changes affect utility facilities and the utility owners are left out. So it is important to communicate design changes to our utility partners so all parties can plan accordingly. When utility issues are not addressed during design, we run the risk of construction delays and increased construction costs. When there is a lack of communication and the project is too far along, there may not be enough time in the project schedule for the designers and or utility owners to reassess the utility conflicts and redesign. I've seen designers and project managers with the mindset that utilities can just relocate, mainly to maintain a schedule or reduce rework. And as a former designer, I was guilty of that mindset myself. Unfortunately, I am reformed, but it was through having the knowledge of utilities. And I have seen this transformation with other designers as well. So this is where the use of SUE and 3D technology can be used. Here at GDOT, we promote SUE, and within the past 5 years, we performed SUE on about 60% of our roadway projects. So it has become a more accepted practice. Our utility offices have implemented processes to enhance coordination between our utility partners and designers. So GDOT has seen improvement in utility awareness, but of course it's a process. I've seen that environmental, right-of-way, and utilities are 3 main contributors to design issues and schedule delays. Environmental and right-of-way are difficult to get around, so designers are often forced to look at these issues. But with the proper tools, designers can be more mindful of utilities when designing, just as with right-of-way and environmental. So with the use of SUE and 3D technologies, the designers can have a tangible product that can follow the project so the designer can continually reassess utility conflicts in an efficient way and not rely so heavily on the utility engineer. So with that being said, I will let Evan explain SUE and the use of 3D technology.
Awesome. Thank you, Chanel. I enjoyed the last presentation that was given, and we're going to kind of dive a little more into utilities, obviously, here. So as a lot of you know, we're keenly aware that the transportation industry is embracing 3D design software such as Bentley Open Roads, which we will be focusing on today. In making this transition, we're getting away from 2D submittals on paper with those big roll plots spread on a table into more creative ways of depicting what we are designing, i.e. new visualization methods such as augmented reality. And it's definitely been exciting to me to see how the creativity is being brought to the forefront and encouraged as we dive into 3D design. In doing so, we need to bring our utility submittals for design projects into 3D as well. Our group here has been working for the past couple of years, performing some pilot projects, and we've gotten some positive feedbacks on the stride that we've made, and we want to share those with you today. The following slides will dive into Bentley Open Roads functions in 3D utilities as well as visualization. Joseph, I'm ready for the next. So to briefly summarize what to take away from this, first we'll quickly review subsurface utility engineering, or SUE, and how utility information is depicted. And then we will go and learn how to create a 3D utility model from 2D SUE data. And then we'll talk about something called clash detection, which allows for us to more effectively identify utility conflicts, and then finish by talking a little bit about what a reality mesh is and how that plays into 3D design. I'm ready, Joseph. So before we get into 3D utility drawings, I'd like to take just a minute to talk about our basis in 3D utility drawings by talking about what SUE is. So SUE was standardized by ASE 3802 all the way back in 2002, and it states that SUE is a branch of engineering practice which involves managing certain risk associated with utility mapping at appropriate quality levels. What I take from this is that I like to refer as quality levels as levels of confidence we have in the utility information that we're depicting. So in this slide here, we're showing quality level D SUE. We're showing some electric lines, telephone lines, gas lines, and the associated APWA color coding, which is used nationwide. The line style only has a letter on it representing the utility type, or it may have a D in parentheses, as well as is placed from a variety of sources that include records and site observation. Additionally, typically, overhead utility line work is shown with a slightly different line style. As you see on the bottom of your screen, we have a line with electric, telephone, TV, and traffic control. And the way we usually depict it is to combine all of those into one line style. Typically, overhead utility line work is classified by state DOTs as QLD SUE, although some classify it as QLC. I'm ready for the next, Joseph. Thanks. So quality level C indicates that we have two surveyed utility appurtenances that quality level D records show has utility line work connecting the structures. In this case, we have two sewer manholes at the bottom of the screen there that are connecting sewer line work. As noted in the exhibit here, we have a parenthesis C in the line style, which indicates quality level C SUE. Ready for the next, Joseph? So quality level B SUE is where we go and we send our field staff out in the field, into the field to mark underground utilities on the ground with paint utilizing electromagnetic locating equipment. This is usually the most common level of SUE that you see on a plan set, as it's the most requested. If you're walking around, especially in an urban area, you're likely to see these markings on the ground. And personally, I enjoy looking at, I enjoy walking around urban settings because there's tons of utilities, as y'all probably know, underground along a roadway, and it's kind of fun to see what all is underground. But once the marking of utilities is completed, we will then have our markings surveyed and then reduced into a CAD file, and lastly, string quality level B line work between each survey point. The product of this is defined by ASC 3002 as that the accuracy of the utility line work horizontally should be within survey tolerances. This is much more tight than one call utility locating standards, which dictates usually 18 inches to each side of the utility mark. Usually you will see a B in parentheses, as you see in this exhibit here, for quality level B SUE. Ready for the next, Joseph? So quality level A SUE, lastly, we arrive at. This is considered to be the most accurate level of utility information defined by SUE, or more or less a guarantee in 3D. This is where most SUE firms will use air vacuum excavation trucks in order to non-destructively expose buried utilities. As shown in the upper right-hand corner, the result of this is exposing utilities so that we can gather utility data such as depth, condition, and size. Once we backfill the test hole, and as well as needed patch the pavement in which we are excavating if we're working the roadway, we will then bring out a survey crew again to survey a nail that we set in the ground at the location of the center of the utility exposed. Once the survey of the location is processed, we will record the coordinates and the elevation of the utility in a test hole data report. And these SUE deliverables, they have to be signed by either a PE or an RPLS, depending on the state law. So now we've defined what SUE is and the quality levels that are used to depict utility information. As noted, ASC 3002 has been around since 2002, and as for the most part, outside of the ever-evolving industry of the equipment that we use to go and mark utilities and collect utility information, the basic process for how we are depicting SUE has remained the same. As a result of this, we've kind of been in a rut. With only having standards to go off of to create 2D SUE deliverables. As shown in the quality level slides, as more and more infrastructure is built around roadways, there are more and more circumstances where underground and overhead utility line work is placed so that it's so congested that it's almost difficult to read on utility plan sets without doing things such as doing insets to highlight utility line work. With the emergence of 3D design software such as OpenRoads, we have an opportunity to get out of this rut and start to incorporate utilities into 3D design plans. In time, there will be an update to ASC 3002, but for now, we're in beta testing to develop 3D SUE plans. And with that said, I'm going to hand it over to Joseph.
Thanks for that, Evan. I appreciate it. So I'm going to talk about taking 2D utility information and bringing it into a 3D file, 3D working file. So when we're putting together a 3D utility drawing, we need to consider the ways in which we can determine the depth for the underground utilities. As Evan mentioned earlier, QLA test holes are currently the most common way that we do this currently. The process is, I'll bet, time consuming and particular not really cost effective. So we found out that if you employ a series of tasks to associate the utility depths, we can be more productive and more cost conscious. We first start with utility depths that are defined by your state's utility accommodation policies, such as lowest level of confidence in utility depth. We then go and follow the utility information gathered by utility line locators and ground penetrating radar to give us an electronic depth. The electronic depths are going to be your next highest level of confidence in utility depths that involve gathering depth readings that we're then able to ascertain from the electromagnetic equipment used to collect the quality level B information. These electronic depths are relative in nature and often not used, not to be the level of accuracy that would be satisfactory for design and form. Although the purposes for creating a 3D utility model, they're extremely useful determining an approximation of the depth. In addition to these two methods, we can physically search for the project site for utility structures such as vaults, manholes, things of that nature that we can then open in order to collect utility depth data from. Performing the test holes are typically done when we need to basically true up, so to speak, the depth that we have utility depicted at, or if we find later in the project cycle that there's a conflict with a design feature and existing utility more, and we'll talk a little bit more about that a little bit here. Also to note that if you're using LiDAR survey on your projects for whatever reason, the LiDAR has the capability to map the overhead line work as well and incorporate that data into our 3D model as well. It's definitely could be useful, especially when we're looking further into the utility mapping and meshing of the data that Cyrus is going to be talking about towards the end of our presentation here. And there it goes. We utilized some special software called PointMan that we utilized to capture this electronic depth information. It's an application within the SUE industry that utilizes to make incorporating the information into a 3D UTLE file much more efficient. One of the way that we do this is through this use of PointMan. Generally speaking, it's a mobile software application that connects via Bluetooth to Bluetooth-enabled electromagnetic locators such as the Vivax VLOC 3 Pro, which is shown over here on the left-hand side. And it's paired along with GPS devices that are, as you can see here, utility pole here, and then also on this one here as well. Pairs with the GPS devices to help us draw the utility line work on the fly while we're out in the field. To be clear, we're SUE engineers, we're not surveyors, and we're not here to say that PointMan is a replacement for the survey functions required for a SUE quality deliverable. This is more so for capturing our utility data and incorporating that into and supplementing with survey. The use of the technology enables us to effectively and efficiently gather this electronic depth information. Next step here is that we would be then bringing it into the 3D world. We're going to be bringing that, we're able to define line characteristics and utility cells to better visualize what could potentially be in conflict with proposed design and is integral when we're looking at the next steps involving utility class detection, which Evan will be talking about here shortly. One step involving is creating a 3D utility model to utilize metadata that we input into our 3D modeling software, such as Bentley Open Roads, which just all of the slides that we're putting together have been created in. Software such as Bentley Open Roads helps us when we're looking to call out specific details pertaining to how our utility line work is depicted. For our uses in creating a 3D utility model, this would be items such as internal and external diameter or dimensions of a utility, the minimum cover depth of cover, which we'll take from our state's utility accommodation policy, and the level in which the utility line work resides in. For example, if you have a telecom duct bank within the project, typically a duct bank is a series of conduits that are most of the time encased in concrete. Given that you know the dimensions of the concrete encasement, you can then, either from records or from performing the test holes, we can then note in the metadata the outer dimensions of the duct bank as we're depicting it in the file. The only above ground evidence that there is a telephone duct bank along a project, in most cases, is a picture of a telephone manhole, or seeing the telephone manhole out there. It's depicted here on the left-hand photo over here. So this is what we typically see. This is what's actually below the ground, and then we have, the information all shown on the 3D model as well. We also included a reference to what we call pole cones, shown on the image here on the right-hand side of the screen. It's going to reduce the integrity of the pole's footing if there's a utility conflict within that cone of reference of the pole. The key of doing this is the better information you have, the more we can get out of a 3D UTLE file. One of the big reasons for the efforts that we're going through to create a 3D utility model is so that we have the utility line work that is to scale to how it is out in the field. This allows us to better determine utility conflicts, which we'll get into here in a moment. Evan?
Thank you, Joseph. So once we've got a 3D utility file, we can then start working on putting it to use to determining utility conflicts. And the goal of going through the exercises of creating metadata for utility line work, which is basically data about data, and adding utility structures into 3D to a utility drawing, is to create a utility file that not only visually represents what we are looking at with regard to underground and overhead utilities, but also is practical in taking the next steps to determining where there are utility conflicts. This part excites me quite a bit, as if any of you have done what some DOTs refer to as a utility impact analysis or utility conflict matrix. It's usually a very tedious and time-consuming task, and it's very easy to make mistakes doing it in a traditional 2D way. In contrast to this, Open Roads, as discussed in the last presentation, has something called clash detection, which allows for us to automate identifying utility conflicts, which we'll get into here shortly. As noted below, there are a few files you're going to need before you begin. Joseph, I'm ready for the next one. I'm ready, Joseph. Thank you. So before we get into the process of performing clash detection, it is important to identify what clashes or utility conflicts we are ultimately looking for. There are two types of clashes with utilities that we'll look into. The first is called a hard clash, and this is where we have a circumstance where two items occupy the same space. An example of this would be if you have a utility pole that's installed in the middle of an existing sidewalk. The utility pole and the sidewalk are touching each other and thus are in conflict with each other, as you wouldn't want to be walking down the street, not paying any attention, and collide cartoon style into a utility pole. The second is called a soft clash or a clearance clash. And this is where we have a circumstance where we have two items that do not occupy the same space, but they are deemed too close to each other. An example of this is if you set a clearance zone of 5 feet between where you have an excavation trench and where you have an underground gas line. If the gas line were to be 3 feet away from the edge of the trench, then that would be inside of the 5-foot clearance zone and thus would be in conflict. I'm ready, Joseph. So I just want to show this slide real quick. You do need to create a surface terrain model as well as a DTM for En-ROADS. Due to the time constraints of this presentation, can't really go through all the steps of it, but we do have a very informative video that we can share with y'all if you'd like. I'm ready for the next. So to begin initiating running a clash detection, we need to establish what we're clashing. In the tools menu of the clash detection feature, which we will open, begin to look at what data we are looking to clash with each other. We'll select two sets of data to clash. In this case, shown in the set A on top, we're going to input the 3D utility file we created recently there. And in set B, we will set the proposed design features in which we're looking to see what is in conflict with the existing utility structures. I'm ready for the next. So once the parameters for the two sets of data to clash are set, we're ready to begin the clash, ready to begin the clash detection. On the right, there's a menu for performing the clash detection, and the result of the clash detection is now shown. Typically, depending on the size of a project, this takes perhaps a minute or two. The data is displayed as a table with the type of clash mentioned early in the center, as well as either it's being a hard or clearance clash. When you are looking through the clashes that is generated, one thing to keep in mind is that if you have an item that, let's say it's a telephone line that is now above ground that's supposed to be buried after a proposed cut is taken from, let's say, station 10+00 to 20+00, the clash will highlight this conflict at multiple locations along this range of stations. So you have to weed out some of the multiple clashes, as we want to say that this telephone line is in conflict from station 10+00 to 20+00 instead of continually calling it out in whatever intervals you set. I'm ready for the next one, Joseph. So a really neat feature of performing the clash detection is that you can create a markup for each individual clash. Shown here are the steps that are needed to do this. And I point this out because this is really effective if you're leading a, let's say, a utility relocation meeting with utility owners for a roadway project. Given the world we live in with COVID affecting our workplace in various degrees, it not only effectively communicates the utility conflict to discuss, but also provides valuable education for utility owners as well as design engineers. A lot of times in these meetings, in my experience, it seems like there's some confusion in what we as utility consultants are communicating with utility owners and our client. And having these markups allows for us to go from utility owner to utility owner and effectively discuss each conflict. I'm ready for the next. So shown here is what a hard clash looks like. Here we have a pole cone that is in conflict as well as a pole with the proposed sidewalk. And as you can see, the pole is touching the sidewalk. We can input the data that the clash detection produces for this individual clash as shown above. We have the clash or conflict number, the type of clash is hard, the location or coordinates of the clash, and the two items that we are clashing against each other. I'm ready for the next. So shown here is what a soft clash looks like when you create an individual clash markup. And in this case, we have a gas main, which is in conflict with a proposed sidewalk again. We set the clearance zone vertically for the sidewalk to 3 feet, and this gas line was shallower than 3 feet, thus it is in conflict with the sidewalk. As with the hard clash, we again have the clash number, type of clash, location, and what two items are in conflict. All right, for the next. So shown here in this data sheet here is the clash detection, what it produces, the raw data. Boxed in red, you got the clash numbers, description, type of clash, and utility and location coordinates. Using these, we can then populate a spreadsheet that most DOTs have for identifying utility conflicts. The point of this exercise is how we can look to identify utility conflicts and also spend more time on what the utility impact analysis or utility conflict matrix is for, and that is determining how we're going to resolve utility impact. So now I'm going to hand it over back to Chanel.
Chanel, you're muted, Chanel.
Oh, thanks. Glad I didn't get too far. So, as stated earlier, providing utility information in 2D has its limitations. We aren't seeing the whole picture like we can in utility information. The main driver of why we do the utility impact analysis is to mitigate utility conflicts. So by utilizing an automated clash detection, we can accomplish this, as it takes a few minutes to find utility conflicts instead of the many hours, if not days, that it could take to do it the old-fashioned way. So I feel that a well-executed 3D utility file and a clash detection can help to accomplish this, as it serves as a great visual to show the utility infrastructure and the impacts to a project. So as utility engineers, we want the end user to use this information more. But in order for this to be successful, there has to be education to all personnel that receive this information. One, about the utility information provided, and 2, how to apply this information to accomplish their goals. So we aren't, replacing the utility engineers, but we're trying to involve additional critical personnel. So another thing is that, which I'm sure many of us have experienced, is design plans tend to change as the project evolves for various reasons. So being able to quickly identify how these changes can affect existing utilities allows for design teams to be agile. With having clash detection, you don't necessarily have to be a utility professional to run a clash detection. So this allows for designers to be able to modify their design after a 3D SU file is complete to quickly determine utility conflicts. This is important as the old process for going through SU and utility coordination involves SU being done first, then doing a utility impact analysis or utility conflict matrix, and then handing it over to the designer to evaluate changes to their design to accommodate existing utilities. So utilizing clash detection, we can save valuable time and cost toward relocation of utilities, which is ultimately the end goal. So with the tools and open roads that we have described, we want to make utility coordination activities happen sooner in the project cycle and throughout as needed. So now that we have discussed SU and 3D application, I will pass it on to Cyrus to discuss another product that can be used to provide 3D SU information. There, Cyrus.
Hi, thank you. Thanks, Chanel. That was a great introduction into what we're talking about and why this reality mesh is so important. Let me share my screen. We'll go to project. Enjoy. We're showing you guys and is our pilot here really for seeing how reality mesh can play a role in QA/QC communication, supporting the process in a lot of ways, especially for utilities. So what is a reality mesh? And to describe it, a good way to start is go to Google Earth. And if it's a city, you'll see they'll have 3D buildings and whatnot. But everywhere they have orthophoto. And really, we heard earlier how you can export to Google Earth with a KMZ file. And it's another way to visualize your design. And it's a 2D product we're used to having, aerial, all over the place. And here's the project in Houston County, Georgia, Big Indian Creek, in replacing this bridge. And there are a lot of utilities involved. So what you see here is a traditional product. A reality mesh is basically that same product, but in a 3D form. So before I go to there, here's an area of the project I'm going to show you in the reality mesh. You can see there's some construction going on there, and there's some utilities here, sanitary and water, all kinds of stuff. But you only see so much. And in a reality mesh, you're going to see in an understandable way. So a reality mesh is now an attachment. I'll move my reference out of the way for you. So if you were to look at a traditional, the surveyed lines that we get in 3D coordinates, this is our team produced this for the project also, you'd see something like this. And if I was to turn that off, there's the utilities. But as you can tell, it's in a sea of vectors, and it's hard to really see anything. So what we did in our pilot was see how we can do a reality mesh using the drone photos that our team for the survey had already collected, which is for the photogrammetry that they did to get all the data out here, where they need for drainage and all kinds of study further away from the road. So we have drone photos, and then the reality mesh makes it look, turning that on, let's turn the topo off. And so right away, you can actually see the two different items. And that's kind of how, except of course in here, you're in a 3D space. So you can see building fronts, and it's all dependent on how well that drone flight was done in order just to get and capture all this information. And recall, I was kind of talking about this area here. And look, lo and behold, there's actually significant new information out there that was in the photos that we sent to capture with a reality mesh. And that showed up. So if I turn on our topo, that at an earlier time when this was created and put together, this whole development wasn't there yet. And it's just one example of how the data of a reality mesh can provide an insight in QA/QC in a very general way to give you the latest info that's out there. And you can see the road change there. And it gives you a QA/QC on your whole survey, which is the context for what your utilities live in. Everything is living in this 3D world that as roadway designers, we're relying on that to get it to come out right. So when I go back to reality mesh only in utilities, then you take it further and you model. It was cool. We had a nice open roads discussion right before this. And there is how we kind of go about modeling a project, the main line and then the intersection models. And so now you're seeing how things work together a little more. But of course, most important is the underground drainage. While having a library here and being able to see it and kind of look at the whole project, and things will jump out at you. So not only you got clash detection where you're able to run the computer, but to give you data and find things, you can also use your eyes and also put it in context. Like, because a lot of the times in the things we saw earlier in this presentation, you'd have, okay, this is a clash, but where does it live in the whole scheme of things? Going to what Chanel was saying, that will give more insight into how to solve a conflict problem. So like, this is an early version of this project, but we could see this conflict very quickly. And we know that we have to do something different here. Additionally, you can even see things like, if you look closely, the transparency. Well, the reality is transparent. And I can see how this is poking out and this pipe is kind of poking out. And it's a layer. So we saw earlier too, great presentation showing public involvement, renderings and whatnot. And the difference here is this is kind of in the guts of it. And it allows the designers and everybody to look at something like real quick. And it's not about this kind of view that you're looking at is what we're promoting for like constructability review, just people getting together, talking, what are the issues right now and getting to resolution sooner. And thereby, saving money, of course, for the overall construction cost. So I guess here is your example with utilities, reality mesh, and a project. I think we go back to the slideshow here. Let me stop sharing. Could you put the slideshow on, Joe? Thanks, man. And because the question is, okay, this is a reality mesh for one use, which is we're pushing. We think constructability, utilities, seeing it all in context, is very important. So, but now let me give you back up further how we're looking at reality mesh for other purposes, and example of that you can create. Actually, I was thinking of having this. If you can see on video, here's the camera I took for these shots here on the road near my house. So we're looking at, for inspection purposes, reality mesh being a more thorough inspection. And on a bridge, that can sometimes be really important, save people, a lot of safety issues, as well as keeping economy flowing, not having sudden closures all of a sudden. So if you are an inspection tool to use it, and you can see on this road, it almost looks like there's no cars, but one of the things it does is it just takes multiple photos. So I had my safety vest on, of course, but went out there and took photos like a robot going across this. So pretending that you need to have that overlap, and you're not taking photos like a regular person. You're taking many, many photos. And that's what you see floating across the bridge, are the cones of my photos. The product I'm using is called Context Capture, and it's a Bentley product. And that's, we drew ourselves to that because it integrates in, as you saw, with MicroStation, with all the design data. So there is Pix 4D, there's other products. So yeah, this is an example, and go to the next slide and show you a little more on this example. So having, oh, go down a couple more, actually. We'll skip this because I covered it, and skip that because these are videos that were choppy. Okay, this is the still image. And so that's the same bridge, and you can see that the model captured a deflection of like 2 inches in the bridge there. So here's again those camera cones inside of Context Capture, which to give you a little more on how it works, it's photogrammetry. So it looks and identifies common points in all the various photos, and then it basically makes control, like points out of it that are 3D that it estimates and forms the model out of all mathematics, basically. Now you take a model, if I'm doing it for inspection purposes, the registration of like it being an exact state plane coordinates is probably not as important. If you're doing, because you're just really trying to show that item. But in the project we saw before, then the registering of that into coordinates is really key. So that in that case, that's why the project in Houston County worked out so well, was that it had surveyors already collected that data, and it basically had the ingredients to let that mostly automatically get done. So yeah, next slide, Joe. So we've seen on foot with the camera I showed you, the Nikon, and by the way, it wants to use a very high resolution camera with a big sensor like an SLR, or it really helps it to detect the matching points. And one other example that we've tested here is the cameras that are mounted on top of our mobile system. And we've done those as well. So there's three ways to get reality mesh, a lot of different uses, but focus on, for today was clash detection, communicating the bigger picture of the context of all of this design that's going on. So I think next slide, pass it back to you, Evan or Chanel, or any questions that people may have. We'd like to take those.
Yeah, I see a few in the comments. Samantha, if you want to go through them here.
Dom will be your facilitator for this. So Dom, you're on. Thank you.
Okay. So which one do we want to answer first here? Have facility owners, especially larger national ones, been involved in the 3D design implementation?
Hang on, Evan. Sorry.
I'm sorry.
Dom.
Is Dom going to be?
Yes, Dom's going to facilitate these questions for you.
Okay.
So let me just make sure he can turn on his microphone and camera.
You could hear me?
Yes, can hear you now. Yes.
Okay. So thank you for that presentation, everybody. Very informative. We have 4 questions right now. And as we read them from the top down based on how many votes the attendees vote on. So right now we have 1 question with 2 votes. And the question I'm going to address to the group that spoke, and then you could decide who will answer the question. Have facility owners, especially larger national ones, been involved in the 3D design implementation? That's the first part. Most facility owners will provide existing data in 2D PDFs or even hard copies. I'll leave that to the team.
So I guess I can answer that one from a GDOT standpoint. So what GDOT has, we have quarterly meetings where we meet with our utility partners. And so we have recently made the utility owners aware that we will be performing 3D SU on upcoming projects to more so gauge their interest. There's definitely, there was some apprehension for some utility owners, whether it's, the use of software and just the use of, MicroStation. And as mentioned in the question, there are a lot of utility owners that still use PDFs. So what we are doing with GDOT, we have actually took the initiative to start doing some 3D SU, so we can actually show the utility owners and the designers the usefulness. It's easier to get buy-in if you have a product and show them how they can use it. So that's more of the route that we're going. So I guess in short, they haven't been involved in the implementation at the moment. They're aware, but once we can show them how it works, we do want to get their feedback. And as far as the PDFs, so in En-ROADS and MicroStation, we have this program that we use. It's called Navigator, to help with those utility owners that don't actually use MicroStation. We are trying to see what we can do with the with the open roads to address that situation. That's still an ongoing thing. So we're actually really early in our 3D design. So we definitely have some things to work out. So
yeah, I can add to that on a national level a little bit. The DOTs really set the stage for a lot of the utility ownership to be able to implement new technologies and things of that nature. So with the DOTs, a lot of the DOTs across the country are beginning to implement more and more 3D information. And as more and more DOTs start requiring that on their projects, a lot of the facility owners are going to start following suit and trying to capture their information on a 3D platform as well. And the data that's provided from the facility owners can be converted into 3D with some more investigation, so to speak. So the information that's provided from the utility owners is not necessarily obsolete. It's very very intuitive, and it's a really useful tool to have. But it's we're expanding upon it with what we're doing, and as the technology continues to advance, the product that are coming out of the information is just going to continue to grow. Did that answer your question?
Yes, that's a good answer. Anybody else from the team want to expand on that question at all?
I think I'm good. I think that was beautifully said.
Okay, very good. On to the next question. How would you differentiate between the different quality levels of the 3D models, specifically for local LEP projects without SUE?
You mean with a note? Go ahead, Evan, but I guess with notes on the plans, I'm guessing.
Well, no, the different line styles they're leveled on. The way we have done our 3D model is we have them leveled at different quality levels. However, if you don't have SUE, you can't have different quality levels.
Can I add to that, Evan?
Well, I'll be QLD really, but yeah, sure.
So
Yep, that's a good answer.
when you're defining SUE, it doesn't necessarily include the 3D aspect. The Z coordinate is not necessarily defined within the SUE standards. So we kind of reference that in when we're talking about a 3D model. So when we're bringing in that Z coordinate to it, it no longer falls under the SUE standards and being able to qualify a line segment as a SUE quality level. The horizontal depiction of that can be at a SUE quality level, but the vertical, we're working with some of the DOTs across the country now to come up with a vertical standard of care, so to speak, to where we're assigning similar to a quality level, but more of a confidence level of the depth depiction of the utility, if that makes sense.
Okay, thank you for
That
that.
also,
Yeah.
Okay,
I think
that also,
that's all the time we have today for questions. I just wanted to say thank you, everybody. Thank you, Cyrus, Evan, Joe, Chanel. Thank you for a great presentation.